Okay, and welcome to Unit 10. This is going to be our plate tectonic unit, and this is our first video probably of three, maybe four. And what we're going to talk about in this one is just the structure of the Earth, which we talked about back in like Unit 3, as well as how it applies to plate tectonics, talking about all the units up and through Unit 9 and earthquakes. And if you take a look, we actually have three views of the Earth. We have the Atlantic view showing you red, which is supposed to be showing you young rock, green and blue being the oldest. And then you can see we have, looking at the North Pole, the Arctic Ocean actually having some young rock. And then we actually have, looking at the Pacific Ocean, the Ring of Fire, which is that line right there. But that whole idea is from earthquakes and volcanoes and mafic and felsic and how rock erodes and weathers and all that stuff. All that has to do with how this planet appears today and how it may change in the future and how it was in the past. Okay, so the first slide we're going to talk about after that is the structure of the Earth, and we talked about this, like I said earlier. And if you take a look at the Earth, we actually have layers, and we can look at the layers chemically, where we actually have the crust, and we have a mantle, and we have a core. And you can look at it physically, where we actually talk about being more solid or less solid. We have that solid outside. We have a semi-solid upper mantle, even a more solid lower mantle. We have a liquid core and an inner core. The core is made out of the same stuff, so chemically we just have the core, and the mantle is made out of the same stuff, and it gets more and more mafic as we go down, more and more iron and magnesium as we go down, and more silica as we come back up. But because of that, we actually have three layers. We have the core on the inside, and we can look at the outer core being liquid, giving us our magnetic field, actually stopping S waves from going through and P waves from going through the way they are supposed to. And we have an inner core, more dense material, so dense because it's hotter than the outer core, but it's more dense because it has the weight of the outer core, the mantle, and the crust all pushing down on it. And you can make solids two ways. You can actually freeze it, slowing down the motion, or you can slam the atoms and molecules together, slowing down their motion and eventually turning them into solids. So core, mantle, and the crust. Crust is what we're going to talk about. That's actually where the plates are, with some upper mantle in there, and we'll talk about convection and the mantle moving these guys around. So the crust. The crust is where we live. It is actually made up of two different varieties. There's what's called the oceanic crust. It tends to be the thinnest of all, 7-kilometer average, so it does get a little thicker closer to the continent. And out in the middle of the ocean, where the mid-ocean ridges are, it may actually be more like 2 kilometers. It is the densest of the two. If the two meet, not consistent on the same plate, but if one plate runs into another, this one being more dense will be the one that's going to sink down underneath it. The reason it is more dense, it is mafic. It's made out of magnesium iron. And it also tends to be the youngest. The oldest oceanic rock is almost 200 million years old, maybe a little older than that. Continental crust is a lot thicker, up to 70 kilometers. Works out to about 40 miles thick. That's where the mountains are. The higher the mountain sticks up, okay, so I just had a student drop by, paused it, and coming back. Continental crust is thicker, so like I said, 40 miles thick underneath the mountains. Where the mountain sticks up, it also goes down. It's like when you stand on a rowboat. When you add your weight to that boat, the boat sinks into the water to compensate, to support the weight. It's called buoyancy. It is the most buoyant, so when the two, oceanic and continental, run into each other, continental is always the one that rides up over the top. And because of that, it doesn't get recycled back into the mantle. It tends to be the oldest, and you can actually find rock that is 3.8 billion years. 3.5, you find more of it, but you can also find new rock in the continent as well. Okay, go to the next slide. How do we know what's actually in the Earth? That's ending the sentence with a preposition, bad sentence. It's all geophysical surveying. It's looking at seismic waves, where the P waves come through. There's a P wave shadow, so we know that there's actually some sort of a change in density in there. We actually have what's called an S wave shadow, which is down here, and that actually tells us how big this core is. We're never going to get down there, at least not with our technology today. It's way far, 6,000 kilometers away, way hot, hotter than the surface of the sun, and so much pressure it would crush you to probably the size of a baseball. before it incinerated. Actually, you'd probably get incinerated first. But anyway, we use seismic waves. We also use gravity studies. We take ships, or we actually do on land too, and we can discover more dense material underneath it or less dense. Magnetics, we can find north and south poles. Find the strength of the poles. Electrically, we can use conductivity to run electrons through. Some materials are more conductive than others. And we can also look at geographic maps, excuse me, which is what this is. So acquisition by land, by sea, and we're finding out now satellites can tell us a whole lot. We can also have geologic surveys, field work, go out and study things. We can drill holes, and we can go into mines to take a look at geology. And the last slide we're going to talk about today is what is plate tectonics. If you look at a map of today, don't pay attention to the ocean, because Alfred Wagner way back in the 20s had no idea what the ocean floor looked like. That didn't come until World War II looking for submarines. We'll talk about that a little later. But if you start looking at the shape of some of the continents, especially like Africa and South America, they look like they fit together. North America and this coast of Africa, North America, Greenland, and Europe. Then we actually can pull Australia, a little weird shape, and Antarctica, a little weird, but they actually have homes for all of these things. But start looking at that in the lab we're going to do today in class, or depending on when you watch this movie, what we're going to do the day after we do the test, which is tomorrow. The next thing we're going to do is a Pangea lab. We're going to do one doing the way Wagner did it, and two, we're going to actually do it the way he finally figured out when he actually found some evidence. I do want to show you a shock wave. This is, you can't see the whole thing. Let me see if I can enlarge this. Looks like I can't, but I've got a static map and I've got labels, and I'm going to push play, and you guys are going to see these things move around. And as you can see, they're moving. Okay, now a teacher just came in, so I had to pause it again. Don't know where we are yet. If I take this back, Pangea breaks up about 225 million years ago. If you notice that North America and Africa split, and that's the birth of the Atlantic Ocean. Florida probably wasn't there at that point. You can start seeing some of the familiar shapes. That's India. There's Madagascar, Australia, New Zealand, Antarctica. This is going to be the Arabian Peninsula once it breaks. It has a divergent, which we'll learn later on. Divergent boundaries split things up, and as North America moves this way, this is called the Tethys Sea. It will become the Pacific Ocean. It's actually going to push itself over, being a felsic continental crust, push itself over the mafic oceanic crust, and it's going to cause all kinds of problems for the western part of the United States. When North America slammed into Africa, created the Appalachian Mountains right here, we picked up some of Africa when we split, but it made the Appalachian Mountains, and they were supposedly taller than the Rocky Mountains are today, which is caused by this convergence over on this side. Okay, I think 8 minutes and 30 some odd seconds is enough. Appreciate you stopping by, and we'll do, like I said, a Pangea lab in class, and then we'll move into the divergence, convergence, the plates actually moving around. Again, thank you. Bye.